I would like to uh, talk about the fourth phase of water beyond solid, liquid, and vapor. Uh, when when you hear about water, the first thing that comes to mind is don't we already know everything there is to know about water? And I'd like to start my presentation by demonstrating that that's not all the case at all. I'd like especially to focus on how water is influenced by light. But first of all, what do we know about water? Well, the first is a cloud. We see this all the time. And the question is, the cloud is made of water. Water is heavier than air. What makes the cloud float in the air? Perhaps you've never thought about it. But this is a really important point. Next is about water forming a bridge. So here you take two beakers and fill them practically to the brim with water. And you stick one electrode in one electrode in the other, and you pass a current between the two. And here's what happens. It's a high voltage. And you can see that a bridge forms between the two. But what's really interesting is if you move one beaker away from the other beaker using a motor, you can see that the bridge persists. And it persists essentially indefinitely for a span of up to 3 or 4 centimeters. What's the explanation? Can we understand? And here's another one. This is a lizard from Central America sitting on a branch. And when it gets the, shall we say, the urge, it jumps from the branch. And this is what happens. Effectively, it jumps into the water and it walks on the water. And so, of course, the question arises, it's called, by the way, the Jesus Christ lizard because it walks on water. And the question is, well, why does it walk on water? You know the answer. Not everybody does. And here's another experiment that really intrigues me. It's a trough of water, and it's dyed red for effect. We'll see in a moment. Behind the water is a superconducting magnet. When you turn the magnet on, the Red Sea splits as though Moses could walk across it. What's the explanation? There are many phenomena whose explanation we really don't understand. We basically don't understand water. Well, I got my inspiration. I was in a different field dealing with muscle contraction from a guy named Gilbert Ling, who died recently, and Gilbert was a great inspiration to me. He wrote many books. His books were largely focused on water and the idea that inside the cell, or in biology in general, that the water molecules were not exactly like liquid water. If we take liquid water in a glass, the molecules are bouncing around randomly at a furious number of times per second. And he said, no, that's not the case. Inside the cell, the water molecules are lined up. He called it structured. I found myself intrigued by that. It's what got me into the subject of water. I gave his books to some of my students, and they fed back to me, and uniformly they said, this guy is on to something really important. Pity that he didn't quite make it to his 100th birthday. Anyway, it's what set me on a course of studying what Gilbert Ling had to say. And we knew from Gilbert's work that inside the cell, there were many proteins and other surfaces, charged hydrophilic surfaces, and the water molecules lying next to those surfaces. And the water molecules here, each one is represented by a dipole plus and minus. And Gilbert's idea was that because there are these charges on the surface, the water molecules line up, as you can see here, and they may line up in multiple layers, organized in a certain way. And of course, eventually, the idea of Brownian or thermal motion will disrupt any kind of order. But for a reasonable span, Gilbert argued that the molecules are organized. And we're talking about many molecular layers, not just 1 or 2 or 3 shown here. So this is kind of like a crystal. And And we know that crystals have a tendency to exclude impurities or solids, solutes of any kind, and that's what makes them pure, because they have this capacity for exclusion. So we were looking for an experimental preparation that we could use to explore this phenomenon, and we knew that we're looking for some region of water that excludes solutes or particles, and we found it rather quickly. So here is a chamber, and we put a gel into the chamber, and here's the boundary of the gel. And we put particles in the water. These particles are little spheres called microspheres. And looking in the microscope, we could already see that there was a zone where these microspheres don't want to be. And we could actually watch the video. This is a span of about 5 minutes. It's sped up. And you can see that this zone here extends for about 50 micrometers, which is a pretty large span. We found much larger zones. And someone suggests that we should give this a name, because apparently nobody had found this before. But in fact, there was a paper published in 1970, 50 years ago, that demonstrated pretty much the same thing. Anyway, we called it exclusion zone, obviously, because it excludes water. It excludes, microspheres. And for short, we call it EZ water. You know, it works. It's easy to remember, but it works in the US because exclusion zone, EZ. But unfortunately, in most countries, it's EZ. So it doesn't work quite as well. Anyway, we discovered a region that we thought was possibly due to the ordering of water molecules, a crystalline-like structure that excluded the microspheres. And this was a rather long-term exclusion. So in terms of the generality of a phenomenon, we could find this not just with the gel that I showed you, but many hydrophilic substances. So long as they're hydrophilic, that is water-loving, in other words, if you were to drop water on the surface, the water would spread out, right? As opposed to hydrophobic, fearing of water, like Teflon, where it would beat up. And we found in many experiments that many solutes and particles and such were excluded. So this is a rather general phenomenon. So the question is the water in this exclusion zone water, is it really different from bulk water? And we did many experiments, and here's a list. I'm not going to go over this in detail because there's too much, and it's published mostly, so anybody interested could go over it. But there's a list of features that we found which indicated that this zone, that the water inside this zone was distinctly different from any ordinary kind of water. And I do want to talk about this issue about the negative charge, because it's pretty important. And the idea that the exclusion zone typically has a negative charge. So it's illustrated by this diagram. So here's a material whose surface is hydrophilic, and there's water next to it. And the EZ region, or exclusion zone region, is, as I said, typically negatively charged, and the region beyond is positively charged. So it's like a battery, separated charges. And it makes sense because we found later that the way this is formed is that the water molecules that are originally in here, as soon as they meet the surface, they undergo change. And the negative part of the water molecule, the water molecule splits, and the negative part forms this EZ, and the positive part is out here. So it's kind of like a battery, separated charge, and indeed you can get current from this battery. And this illustrates the way it actually works. Here's the water molecule with an oxygen and 2 hydrogens, and the water molecule is actually split, and I'll explain to you in a moment how and why. And this part this is the negatively charged part, 2 minus, 1 plus, goes into building this, and the positive is sitting here in the water. So the way it works is this way, which we were able to deduce from additional experiments. Here's the hydrophilic material sitting next to water, and the easy layers form one at a time. And we found that these easy layers, it's actually a honeycomb structure, hexagons that fit here, and they build one by one, starting at the surface and building out. And here's another, and so on. And if you look at the surface in a bit more detail, the oxygens appear at the vertices of these hexagons, and the hydrogens appear in between those. And if you were to count hydrogens and oxygens in this structure, it's not H2O. It can't be H2O because we found the negative charge, and H2O is neutral. So we found actually it's H3O2 is the chemical formula of this easy water. Now, inside your cells, my cells, it's crowded, because it's crowded with solids, mostly proteins, but other solids, including nucleic acids. There's actually not much space left for water. Actually, it's a very narrow space. It's not exaggerated here as it should be, but these solids really pack the cell with not much space left. So all the water is essentially interfacial water. That is, all the water, almost all the water, is very near one of these hydrophilic surfaces. So you would expect that that the cell would be filled with easy water, and that is indeed confirmed in various experiments. So your cells, my cells, all of our cells are filled not with H2O, but mostly with H3O2, with this kind of water. And that's why if you cut a cell, if it's liquid water, it would just leak right out. And you know, every time you've gotten the cut, the water doesn't come gushing from your cells. It's more like a gel. This easy water has gel-like characteristics, and it stays in, even if the membrane is broken. Now, the issue arises, some people may know about water memory. Water memory is an issue that inspires great doubt, because how can water store information? But if you think about it for a moment, in relation to the discovery that I'm detailing for you, think about a thumb drive and how it works. Inside the thumb drive, you've got silicon, and the silicon is arranged in a regular, orderly way, not just in 2 dimensions, but actually in 3 dimensions. So each one of these atoms is situated in a particular spot, and as you know, each one of these can take on 2 different states, either what is called a 0 or a 1, or on or off or whatever. And that's how the information is stored in 3 dimensions. Now, if you think about the EZ and its structure, it's very much the same. It's got oxygens and hydrogens, and I'd like to focus on the oxygens for a reason I'll mention in a moment. And all of these oxygens are oriented in a 3-dimensional array. So you can imagine that if it were possible for these oxygens to take on different states, each one taking on at least 2 different states, we have the capacity for memory inside the easy water. And the person who brought this to light is the late Masaru Emoto from Japan, who was able to focus his intention on water and then freeze the water. And he found that depending on the attention that's applied to the water, the crystal structure would reflect somehow that intention. And this has become very popular, although scientists are reluctant to accept this because mostly they don't understand the mechanism. And in truth, the studies that were carried out by Emoto as a spiritualist, not a scientist, were not done in the most objective fashion. And however, his disciples are continuing along those lines, doing it in using more scientific methods. And so the result looks something like this. If you play a Mozart symphony or John Lennon, and you freeze, you get beautiful crystals. And the same thing about thinking about peace and thank you, also beautiful crystals. On the other hand, this is, I believe it's You Fool or something like this, or heavy metal music, you get ugly crystals. So I'm not 100% certain that this is true, although what I would like to say is that I think there's a good chance that it's true. It needs to be proven objectively. And the basis for this, I think, lies in the structure of easy water, which is very much, which fills our cells, and is very much like a crystal of silicon with atoms aligned in a regular array. And what's interesting about EZ is that the oxygens can take on not two different states, but if you look in any chemistry book, you'll find that oxygen has 5 different oxidation states. The typical is -2, but there's also -1, there is 0, +1, and +2. If you think about that, you can calculate the memory density, at least theoretically, in easy water. And it turns out to be something like a few billion times, or even more, I can't remember the number, greater than the silicon, simply because it's got 5 states instead of 2 states. And it leads to a very impressive increase, theoretically, in the memory storage. So you, yourself, could, in fact, be a storage of information transmitted from other people, for example, or from outside influences. Okay, back to the original question. Is the easy water physically distinct from bulk water? And the answer, as I've demonstrated to you, is yes, it's different. It's a layered honeycomb structure, as best we can identify it, and it has information storage capability. Many experiments have been done to demonstrate information storage capability in water. I don't have time to detail it, but we organized the annual conference on the physics, chemistry, and biology of water, and each year, 2, 3, 4 presentations on this subject. This is an up-and-coming subject of great interest. And of course, it then may respond to intention. So subtle influences can impact water. I mentioned that water, the easy water, is like a battery. It has negative charge with positive charge beyond. And batteries need to be charged. Otherwise, they run down. Your cell phone battery, it won't work if you forget to plug it in. And it's the same with the water battery. It's a general principle. So what charges it? Well, we didn't know the answer, and I must admit, we struggled for a couple of years before finally we found out. And it was a student who was doing some experiments who taught us. He was doing experiments that he wasn't supposed to do, but these experiments taught us where the energy comes from. And the energy comes from, actually, from light, or you might say incident radiant energy, light. How did we find out? Well, the student was working with a hydrophilic material known as naphion, and this represents the chamber. And there was a lamp setting next to the chamber, so he grabbed the lamp and shined the lamp on the experimental chamber. And you can see right here where the light is not impinging, this is the exclusion zone. Here are the microspheres, and it's pretty uniform, parallel to the surface. But where he was illuminating, you could see the exclusion zone grew. And I suggested to him, why don't you remove the lamp, see what happens? And sure enough, it went right back to the original when he turned off the lamp, with a time constant on the order of tens of minutes. So from that, we learned, it didn't take a rocket scientist to figure this out, that light, photons from light, constitute the energy that's responsible for building this exclusion zone. And through experiments, which I won't detail because too much detail, the most effective was infrared. And infrared is all over the place. We think of infrared as coming from, say, from the coils of an electric range. You know, they generate heat, they're orange, we say they're generating infrared energy. But in fact, infrared comes from all over the place. And if we were to darken a room so that neither our eyes nor our cell phone cameras could pick up any image at all, an infrared camera, that is a camera with an infrared sensor, could quickly pick up all images. So basically, the bottom line message is that everything is generating infrared energy. And that means the energy is always there, which means the EZ should always be present. And I believe it is all over nature, especially our bodies, but all over. So we have a situation that looks like this. We have a hydrophilic material sitting next to water, and because the infrared energy is always available, we have a certain amount of EZ water, and the rest is just ordinary water. And if we, if we add infrared energy, more infrared, it grows the EZ. We've seen it grow by as much as 10 times. And if we remove it, it goes back to the default or the original. So the bottom line is that the energy comes from light and mostly from infrared light. So EZ buildup is powered by photonic energy or light, which orders the water. You need energy to create order, and charges the water battery. You need energy to charge the battery. So basically, if you're sitting on the beach, either in Busan or in New York or wherever you like, it's just a matter of lying on the beach and absorbing the sun. You automatically get recharged just by exposing yourself to the sun. Now, if the scenario that I illustrate here is valid, you kind of would think that if this is receiving energy all the time, you should be able to harvest that energy. And the question is, do you? And the answer is yes. This is another experiment by a student. And the student, we found out that Nafion, this wonderful material with hydrophilic surfaces, creates very nice EZ. We found that it comes in tubes, not just in sheets. And you can see a tube that's sitting here. And Arthur was supposed to look and see if indeed, if you put the tube in the water with particles, microspheres, can you really see an exclusion zone inside and maybe even outside? And the answer was quickly yes. But Arthur discovered something else. And one day he came running into my office. He barged in without knocking or anything. And, you know, I usually don't care. I was sitting with an important visitor at the time, and it was kind of rude, barging in, but he told me, he said, you know, I see something that looks really interesting. And I wanted to tell you because I'm excited about it. He said, I see that when I put the tube in the water flows through the tube and it just keeps flowing. It doesn't stop. He said, I thought that was interesting. Well, he thought it was interesting. And I thought, if it's really true, this is amazing because you need energy to drive the water through a tube, sort of like you need energy to drive the blood through your vessels. And so I thought, so we checked, of course, to see, and it really was indeed true. And this was evidence that energy is coming from somewhere. And we knew that the water was absorbing infrared energy from the environment, which builds EZs, which we thought might be responsible. So the experiment looks like this in video. And you take the tube of Nafion, you put water inside it, make sure there are no bubbles, and then put it into a bath of water containing microspheres. Look in the microscope, and we used green light to minimize the overall light exposure. And this is what you see inside the Nafion tube. You can see the exclusion zone sitting here and here, and it just keeps going. We've had it going for a day and a half. Someone suggested that maybe Nafion has special properties that give rise to this. Could you demonstrate it in other preparations? And we did. So this is a gel. Here, this polyacrylic acid gel. Here's gel material, here's gel material. And when we formed the gel, we put a wire here, and as the gel was gelling, we pulled the wire out. That left a tunnel. So we got a block, we have a block of gel with a tunnel running through it. And we immerse it in water plus microspheres. And so the first thing that happens is an EZ builds from this gel surface, as usual, same thing here, and it pushes the microspheres into the center. And if you look at the dynamics, you can see it flows just the same as the Nafion. By now we've we've explored at least a half a dozen gels, I think maybe even more, and they all show the same phenomenon. The speed differs, some details differ, but basically this is very general. Someone came to us and said, "You think this is powered by light? That's weird. Why don't you do the experiment, shine more light, see if it goes faster?" I was embarrassed to think that I hadn't thought about this, but we did the experiment and we published the paper, and it turns out, well, there's the video again, but it turns out when you add light that we could see, sorry, I'm looking for, yeah, we published this, 5 times speed increase just by turning up the light. So we're quite sure about this phenomenon. So essentially, to review what I just said, you have a hollow tube, hydrophilic surface, you put it in water, and you get flow, just like that. You know, you don't need any complicated mechanism or anything. It has something to do with the buildup of EZ and the accrual of protons in the middle, which exert pressure and then leave this end or this end. As it leaves, it pulls in more water, and the process is perpetuated. So work is done in a case like this. And of course, to do work, you need energy. And so the absorption of energy by the water, unless someone could think of a different mechanism, we couldn't. It seems to be a necessary condition for this. The energy comes from the light, especially infrared light, that's absorbed by the water. And the water then transduces the light energy into mechanical energy. So it means that water can do work. If you take a glass of water, you think it's impossible for a glass of water to do work. But basically, a volume of water can do work. It can use the energy from the infrared energy from outside and transduces it into mechanical energy. Water transduces light energy. So a question arises, you may be thinking of, does human biology use radiant energy? And you think about Mother Nature, and Mother Nature successfully invented, if you will, plants. And in inventing plants, and also some single-celled organisms, she devised the method of photosynthesis. And step one in photosynthesis is light coming in, breaking water molecules into H plus and OH minus. And that's exactly the same as we found, light breaking water into plus and minus. So very similar to photosynthesis. And in her great wisdom, when Mother Nature took it upon herself to invent animals, she had 2 choices. One is, since animals can forage, they can find food, they can get their energy from the food. And that seemed to be an advance. But in the wisdom of Mother Nature, one would think that, hey, you know, if you've got a successful mechanism that's working, and that worked really well for plants and some single-celled organisms, why not keep it, at least in reserve? Why simply discard it to the waste bin and invent a new mechanism if you got one that works well? So the question is, what did Mother Nature do? And I would assert that Mother Nature may have kept this light-based mechanism in reserve, or to be used together with the food mechanism. So we receive light all the time, including infrared. The sun, half roughly of the sun's energy is in the infrared region. And we receive this, and some of the wavelengths penetrate deeply into the muscle. And so the first idea came, well, maybe in the cardiovascular system somehow this is used, because the capillaries come pretty close to the surface. And the idea actually came from a Russian guy. This Russian I met in Moscow when I was visiting my friend Vladimir Bayakov in Moscow University. He was quick to introduce me to his colleague next door. And the colleague was telling me through translation that there's a big problem with the cardiovascular system. I must admit, when he said that, I was a little bit reluctant, maybe a bit too arrogant, because I had studied the cardiovascular system, the physics and the dynamics, pressures and flows and such as a graduate student. I thought I knew what there was to know. And, you know, who is this person who's going to tell me something new? It took no more than 5 minutes before he had me convinced. And what was the issue? It's very simple. The capillaries in healthy young adults, the size is down to 3 or 4 micrometers. 3 or 4 micrometers is small. The red blood cells that routinely pass through the capillaries are twice the size. They're 6 or 7 micrometers, which means that in order for those red blood cells to pass through, you got to squeeze. Now, squeezing something like a red blood cell requires energy, and this Russian colleague calculated that there's got to be another energy source, because if it really were the heart that was responsible for doing this, the heart would need to generate something like 1 million times the pressure that it generates. That would really be high blood pressure. So even if it was wrong by a few orders of magnitude, still it's a big problem that you can imagine. And there needs to be some other source of energy. So you can see it here in the video. This is a piece of muscle tissue, and this is a capillary, and this is a capillary, and this one, and even this one. You can see the red blood cells. And you can see that they're actually squeezed. So they're supposed to look like this in nice red color, but in fact, as they move through, you can see in the video, this guy's having real trouble. They encounter resistance, and it requires a huge amount of energy to get these red blood cells to flow through. Seems like a possible mistake of Mother Nature, but we know that Mother Nature doesn't usually make mistakes. So there's a reason for all of this. But the point is, there needs to be some other energy. And so after my visit to Moscow, I'm thinking, well, we have a mechanism that we just found in the lab. We found that radiant energy drives blood flow, or drives flow, I should say, water flow. And the question is, might radiant energy help drive blood flow as well? And we were buoyed by the finding of my student Jing Li, who found a paper, an Israeli paper, demonstrating that they did some experiments, and after they finished their, I guess, routine experiments, they sacrificed the mice, and they had a method of a sophisticated method of measuring blood flow, and they found that even after the mice died, sacrificed, flow would continue, and it continued for at least 1 hour. They repeated the experiments 10 times. They got the same result. And they wound up scratching their collective heads because they couldn't figure out what was going on. Everybody knows, quote unquote, that the heart is the sole driver of the blood. But how could flow continue? So it turns out there are actually quite a few papers in the past 100 years, but not many people are paying attention to it. So we did the experiments, and we used a chick embryo, 3 days old, so some of the neurological and hormonal feedback mechanisms not yet fully developed. And here's the fertilized egg with the shell removed, and you can see the vessels here. And Lee was able to image them here and here. So the first thing he did was to stop the heart. And it's easy to do. You basically just put potassium chloride in the heart, and it stops. And he wanted to check to see if there was blood flow. And so this is flow versus time from his experiments. And the first thing that happens is after you stop the heart, flow goes way down. But it's not zero. It just keeps going, even in this odd situation. And then he tested the signature feature of this mechanism that we've been talking about, of flow in tubes, which is adding infrared energy, and it should increase the flow. And you can see here the flow increased by roughly a factor of 3 times, and then when the energy was removed, it went back to the control level. So he confirmed the most central feature of the mechanism that we discovered in the laboratory. And it appears from this evidence, not yet published, that in your circulatory system, in my circulatory system, it's not only the heart that's generating the flow, but there's a mechanism lodged in the vessels themselves that help propel the flow. We don't know how much is that contribution, but it's certainly a contribution to that. So I've limited this to basically, one observation because of time constraints. But I just want to tell you that the suggestion is that we don't photosynthesize the same way as plants, but the first step of photosynthesis we do actually exploit. So it's not just the heart. This is one example. That propels blood in our cardiovascular system, but also the mechanism, the so-called spontaneous flow mechanism, we call it, for lack of a better name. But there are more features that we use based on light. So if you ask the question, where do we get our energy? Obviously, we get energy from food. Everybody knows that, some more than others. But the evidence suggests to us that we also get energy from light. The light impinges on us, and we make use of that light. And it's not just the cardiovascular system, but other systems throughout our body. The light is absorbed by our water, and the absorbed light builds EZ, which gives us energy. Practical applications, I can't end without discussing some practicalities. And the first is getting energy from water and sunlight. So this, you've seen this before. Here's the EZ water sitting next to the hydrophilic surface and the protons. And you'd think that this is a battery-like effect. We ought to be able to get some energy out of it. And sure enough, if you stick 2 electrodes in, we demonstrated that you can actually get energy out. And here's a video showing that. So these are, I think, a dozen or so little chambers, each one containing naphion and a pair of electrodes. This is a switch. And there's an LED, light-emitting diode, beneath this magnifier. And so here's what happens when you turn on the switch. You light the LED. So this is just water and 2 electrodes and light. So there's a possibility that this can be exploited to gain energy for the world based on basically only a renewable resource, and that's water and light. And we hope we have a company that we put together. It's called Fourth Phase Incorporated, and we're working on developing not only this, but also a filtration system. So the idea is getting drinking water from contaminated water. And this diagram shows how it works. So this is basically the filter, so to speak. And you have flow of water, and the water may contain all kinds of junk, as representative junk. We've tried bacteria, viruses, but typically we use microspheres because they're same size, roughly, and representative. And as you know from now, what happens is there's an exclusion zone here, an exclusion zone here, and all the junk, all the shit, so to speak, comes to the middle. And we devised a so-called differential extractor, which is nothing more than a fancy name from 2 concentric tubes. And the central tube collects the junk, which gets concentrated and out. And the peripheral region collects the junk-free region, the EZ water, that comes out here, and you can see. And we've been successful in demonstrating through a single pass, we could get as much as a 200-to-1 separation. And we've also been trying to look at whether salt might be separated. And this is a dream of ours, which we pursued with limited resources and made a little bit of progress. The idea is you can take ocean water full of salt, and if the salt were excluded, as you see here, then the salt could be collected and we could get drinking water from the ocean. This requires no physical filter. We call it filterless filter because there's no filter that gets clogged and needs a replacement or cleaning or whatever. It's simply, the filtration is accomplished through the energy of light, or infrared light. And the places where the drinking water is needed the most, like Middle East, for example, is exactly the place where there's lots of sun. the sun is responsible for creating this separation. So we're excited about that possibility. So I conclude by suggesting that water actually has 4 phases, not 3 phases. We all know about ice, water, and vapor. We learned about it. And what we've identified in our laboratory is what appears to be a 4th phase of water. We call it easy water. Sometimes we call it 4th phase water. And I put it right in this position. And the reason for putting it there is that the structure of the 4th phase, some of you are familiar with the structure of ice, is actually very similar to ice. It's not the same, but it's similar. And we found that if you want to freeze water, you can't go from water directly to ice. You go from water to easy and then to ice. And if you want to melt the ice, you go from ice to easy and then to water. This is a necessary intermediate state. And by understanding this, it clears up many anomalies that exist in understanding ice formation. So we're excited about that. And all of this has broad implications. The central implication is that radiant energy impinges on the water, mostly in the infrared. It's absorbed, and the water converts. It doesn't remain exactly as liquid water. It converts. The more infrared energy you put in, the more easy water that you get. I've given you at least one example of biological implication that is in the area of blood flow. We're excited about that. In chemistry, if you read a chemistry book, some of you find the interpretations maybe a bit daunting and non-intuitive. And I would argue that one of the reasons is that, especially reactions in aqueous solution, there's nothing that appears that is related to charge separation, to easy, to the effect of light, et cetera, et cetera. And therefore, it may be that many of the interpretations of reactions that are going on in aqueous solution need to be revised. Hopefully, make it simpler, but we don't know. In terms of weather, and we all know that clouds are or can be electrified, and it was shown more than 50 years ago, 60 years ago, that all clouds are electrified, not just the ones that issue lightning discharges. And if you listen to the forecast from the weather people, the word charge is, I hesitate to say never mentioned, but almost never, maybe even never. And it's possible that charge is a key variable, and possibly even more important than temperature and pressure. And my next book, which is almost done, deals with various subjects, including weather, deals with the effects of charge. I think this may be central, and if this is taken into account, we may then learn whether or not we need to take an umbrella to work. For health, easy water fills our cells. If you don't have enough of it, your cells are not working well. And that argument appears in my earlier book called Cells, Gels, and the Engines of Life. The centrality, the absolute centrality of water in every aspect of health. If your cells are dehydrated, they don't have enough easy water, they need more easy water. And an easy way toward health solutions is to get yourself more easy water. In terms of food, we like to have frozen food. We like to have, sometimes we use dehydrated foods that get rehydrated. It's nice to know something about the science of what goes on. I mentioned to you also practical applications like filtration, desalination, and getting electricity from water. And we're, as I said, we're working on those issues. So much of this appears in my latest book, which is called The Fourth Phase of Water. It's become rather popular. It's written in language that's accessible. It's scientific, but it doesn't speak in arcane scientific lingo. At least that's what the reviews have graciously indicated. So I'll stop here, and I'm really excited about this event dealing with water, and I wish everybody the best. Thank you so much.